Welcome back to week number 8. Today we're going to talk about some high-level structures of quantum circuits. On the screen you'll see a Scratch program, one I invented myself, thank you very much. The red block doesn't do anything, by the way. Neither does the purple block. This Scratch program looks like all other Scratch programs at a high level. So there's a structure to Scratch programs. When the flag is clicked, some blocks are executed in sequence, and if something is kind of dangling, it's not going to be executed. If something is inside the block, then that will happen from top to bottom unless there's some sort of loop blocks. When you look at a Scratch program, you can kind of guess what it can do a lot from the structure. The same thing happens in quantum circuits. There'll be some template structure, and most quantum circuits will look at a high level like that template. Now, not all classical algorithms look like such a Scratch program, and not all Scratch programs are so simple, but the point is there is a sort of overarching structure that helps you understand a lot about the program. So in this case, algorithms written in Scratch, or in the case of quantum programming, what I'll show you are typical quantum circuits that will all look vaguely like the template. So let's get to the template. So the template will have some qubit registers. So I've drawn 4 qubits, but each of these could mean several qubits. They always start in the 0 state. And we can name them. This could be the data register, and the next one might be the work register, and this one could be the Scratch register, and the final one is the output register. And typically what we see is the data register will have a whole bunch of Hadamard gates, or maybe some encoding of data, and this might be at a high level called the superposition step. And then there is a step that involves some computation. And that might require some additional qubit registers, sometimes called the work or the Scratch register. Some of those registers will contain the output that we want, and some of them will contain just kind of garbage that we don't really care about. And then usually parts of those registers will interact with the output register, and that might include some phase manipulation. And these things might have to be kind of repeated, but before that's done, you'll often see some symmetric part of the circuit that undoes some of the things that were done before, and that's called uncomputation. And this high-level structure will produce some data, and the nice thing about the uncomputation is it will allow those work and Scratch registers to go back to where they started, and then the output register will contain some information, some computation that we wanted to do on the data. So at a high level, this is what a quantum algorithm will look like if you squint really hard at, or not so hard, at a quantum circuit. It will have this overall structure. Each of these components is in some sense necessary, though not sufficient for quantum computation. Obviously, if we don't have superposition and we're doing these digital logic computations that we saw last time, then we're just doing classical computation in kind of a new way, so there's no advantage. Without the superposition and the computation together, we won't create entanglement, And so we can describe each of the qubits independently, and each qubit kind of contains the sufficient amount of data about the whole system. So we need that entanglement to be able to do something that's at least not describable with classical information, not in an efficient way anyway. And we know that if we create entanglement and then perform measurements, we're going to get random outcomes. Those obviously aren't interesting unless we're trying to create a random number generator. So we have to create these phase manipulation. We have to create this phase manipulation so that things can be combined in a way to create interference. And we'll see later on that the uncomputation is necessary to still disentangle things so that the output is in a kind of in its own unique register, and we can measure or perform some further computation. So we're going to see examples of each of these and how they work next.